In this video, I'm going to be building flip-flop circuits. So, all the circuits we've built so far in this series have been simple combinational logic. The inputs directly affect the outputs at that time. For example, when both of the inputs on an AND gate are on, the output will always be on, no matter what. Flip-flops, on the other hand, can remember what you input. The first circuit we'll be building is an RS flip-flop. So, as we can see here, the RS flip-flop is made up of two NOR gates, and it has two inputs, R, or reset, and S, or set, and then we have Q and Q bar, the two outputs. And what Q bar means is this just means that this is the inverse or the opposite of Q. So if Q is a 0, this will be a 1. If this is a 1, this will be a 0. So how the circuit works is, if you remember back to the basic logic gates video, you will remember that a NOR gate, the output will only be on if both of the inputs are off. And you can see we have the outputs of this top NOR gate feeding into one of the inputs of the bottom one, and the output of the bottom NOR gate feeding into the input of the top. So only one of these can be on at a time, because if both of these inputs are 0 and this NOR gate has its input on, then this NOR gate will be off. Now, when we power up an RS flip-flop, it'll be in a random state, because when both of these gates have both of their inputs off, both of their outputs will be on, which will turn their inputs off, so it'll just randomly go into either the Q being on or the Q bar being on. So our two inputs are the set and the reset inputs. If we turn the set input on and leave the reset input off, then this NOR gate will be off because one of its inputs is on. So this Q bar output will be off. And also, there will no longer be a 1 going to this NOR gate, so the Q will turn on. And if we look at our table here, we can see if the set input is on and the reset input is off, the Q input will be on and the Q bar input will be off. And if we have the reset input on and the set input off, then the Q bar input will be on and the Q input will be off. And then the cool thing about this circuit is if we switch both of the inputs back to 0, the outputs will stay the same. So what this is trying to show is, if we say have both of the inputs at 0 and then we turn the set input to 1 and then turn it back off, the Q input will stay on. And that's what makes a flip-flop. It remembers what inputs you use. Now you can see on this final line we have, if both of the inputs are 1, it says disallowed. And what this just means is, by definition, the Q bar is the inverse of Q, and if both of these inputs are on, then both of these outputs will be off. So it doesn't break anything, it just doesn't really make sense because these are supposed to be inverses. So I've built this circuit on a breadboard here, and like I said, we just need two NOR gates to build this circuit. So I have the 74LS02 chip here, which contains 4 NOR gates. So these two switches, we have our reset input and our set input, R and S. And then those go into separate NOR gates, and those outputs from the NOR gates feed back into the opposite NOR gate, and also into these LEDs. We have the Q output and the Q bar output. So if we turn the set input on and leave the reset input off, you'll see that the Q output turns on. And if we instead have the reset input on, then the Q bar input will be on. But as you see, when we turn both of them back to 0, it'll stay in the same state and remember what input we used last. Now, like I said, if we turn both of these to 1, both of the LEDs will turn off, which doesn't really make sense because they're supposed to be opposites. Now, this RS flip-flop is pretty useful, but what's even more useful is if we can save data or remember what inputs we had at a certain time. So if we look at our next circuit, which is also an RS flip-flop, but with a clock, so we have this third input here, it's a lot more useful. So you can see we've added two AND gates here, and the R and the S inputs go through those before going to the NOR gates. And the other inputs to each of those is the clock. So this R input and the S input can only go through to these NOR gates if the clock is on. And why it's called a clock is, in computers, a clock is just something that turns from 0 to 1. Usually it's a regular thing, but in this case it just means that this will often be changing from 0 to 1. So AND gates, if we remember, are only on if both inputs are on. So if we look at our data table here, we can see if we have our clock input on here, it will function, this circuit will function the same as the RS flip-flop. You can see the tops of the tables are actually the exact same here. However, if we have the clock off, regardless of what the R and S inputs are, the output will just be what it was before we turned it off. And it doesn't matter if we change the R and S inputs at this point, as long as the clock is off, it will just stay the same. So I've also built up this circuit here, and you can see the only difference with this is I've just added a 74LS08 quad AND gate chip, and at this point the connections from all the circuits onward will start to get kind of complicated, so I won't really explain them anymore since I already showed them on the paper. So you can see we have our reset, set, and clock inputs. So if we turn the clock on, then this circuit will function exactly the same as the previous one. You can see if we turn the set input on, Q turns on, and it remains even when we turn these back to 0. And if we turn the reset input on, Q bar turns on, and it remains if we turn it off. But if we turn the clock input here off, you can see that no matter what we do with these two inputs, the Q bar input will stay on, and if we had set the Q input on before, that would stay on. So essentially turning the clock off just means that the inputs can't change. And that is pretty useful. So with the addition of the clock, our RS flip-flop can save data at a certain time whenever the clock is set to 1. But if you think about it, our R and S inputs are kind of redundant. You can see in most of our useful times when we're setting the R and S data, R and S are always just opposites. The only time when they're not is in our disallowed state and when we're not inputting any data. So, to make this simpler, we can just have one input instead of 2 and add an inverter for the other one. So we've replaced the S input with D for data, and our R input is just inverted S. So this is called a D-type latch. And what this does, the reason this is called a latch is because it essentially just saves one bit of information. So we put either a 1 or 0 into the D input there, and when we set the clock to 1, that information is saved into the Q output. So if we look at our table here, if the D input is 1 and the clock is 1, Q will be 1. If the D input is 0 and the clock is 1, then our Q bar will be 1 and Q will be 0. And then, regardless of what D is, if our clock is 0, our output will simply be what it was before we changed the clock to 0. So, I've also built this circuit up, and the only difference we have with this one is I've just added an additional 74LS04 chip here, which is an inverter. So you can see we just have our D input hooked up to the inverter, and the uninverted output is simply going to where our S input used to be, and the inverted output is going to where our R used to be. So you can see if we set our data to 1 and set the clock to 1, then Q turns to 1. And if we have our data as 0 when the clock is 1, our Q turns to 0. So we're just saving one bit. And then when we change our clock to 0, it doesn't matter what the D input is. Our outputs will stay the same. So we just have a few more iterations of this circuit to go, but we can still make it better. So at this point, our data can change any time that the clock is 1. And sometimes it's nice to be able to have a little more precision than that. So our next circuit is called the positive edge triggered D-type latch. And what this circuit does is our outputs can only change when the clock is changing. So if we see our table here, what this arrow signifies is the clock input going from 0 to 1. So if our data input is 1 and our clock input changes from 0 to 1, then our Q output will change, and the same with 0. But if our clock input is a 0 or a 1, our outputs will just remain the same. So our data can only change the instant this switches. So one thing that I'll point out real quick is you can see our outputs have flipped around here. We used to have Q on top and Q bar on the bottom, but here they'll switched, and I'll explain that soon. So this is basically just connecting up a D-type latch to our RS flip-flop with clock. So this is inverted. So when our clock is sitting at 0, our data, which it usually is, our data can go into this first flip-flop. So let's say we have our data as a 1 here. When the clock is off, our data will be able to go into this flip-flop or this latch, as I showed on the previous circuit. But because our uninverted 0 is here, it won't be able to go through to the outputs. But the instant when our clock changes to 1, this circuit this latch will no longer be able to change, but the 1 will be able to go through from here into the RS flip-flop. and to the outputs. And the reason these outputs are flipped is because our set input is down here, which connects up to the Q bar output of our D-type latch. If we look at this, which means that it inverts here. So when our Q bar is on, which is the inverted version of Q, then that will set our set. And that's why our outputs are flipped over here. So that is our D-type, our positive edge triggered D-type latch. And of course, I also built this one. And again, we only have 2 inputs here. So, as you can see, when our clock is just at 0, our data input doesn't do anything. And if our clock is at 1, our data input doesn't do anything. But right now, our Q is at 0. If we change our data input to 1, you can see that when the clock input changes from a 0 to a 1, the output changes. And it only changes going from 0 to 1. It won't happen going the other way. And you can see, now that we have our data input set to 0, when we change this, our Q bar will turn on. And like I was saying earlier, our 2 outputs here are switched. So I just switched around the yellow wires from how they were before. So that is our positive edge triggered D-type latch. And the final iteration we have here is a little more complicated. You can see we have, as well as it being positive edge triggered, we also have a preset and a clear. And the reason I have this last circuit, it's not that much more useful, and we probably won't really need it. But the chip I'm going to be using for this circuit in future videos is the 74LS74 chip, which has 2 of these D-type latches, so I just wanted it to be consistent. And you'll also notice that because I'm using that chip, our preset and clear I have a bar here, which means they're inverted. And then these OR gates allow you to activate these, or turn off or turn on these NOR gates without going through the rest of the circuit. So when this turns to 0, when the preset turns to 0, a 1 comes from here, which goes through here, turning off this NOR gate, which turns on this and turns on the Q output. As we can see, when the preset turns to 0, Q becomes 1, and the opposite of that for clear. So if we look at this, we can see that because these are inverted, while the preset and clear are 1, our circuit will function exactly the same as it did here. You can see the top of this table is identical to this one. But when our preset input goes to 0, regardless of the data and clock inputs, our Q will turn on. And when our clear goes to 0, our Q bar will turn on. And these states will remain even after we turn the preset and clear back to 1. So these can be used to set the D latch before we start using it. And finally, you can see if we have both of these 0, so both the preset and clear active, that is a disallowed state, just because that would make the Q and Q bar both 0, which doesn't make much sense. So I've also built this circuit, and if we hook it up to power, you can see our preset and clear inputs are both set to 1s, which means they're not active right now. And in this state, Our D latch works exactly the same as it did previously, but if we set our preset on, it doesn't matter what these are, our Q will turn on, and even once we turn this back to 1, it'll stay on, so we can preset our circuit to be a 1. And if we do the same with clear, it will turn off, so we can clear our circuit. And like I said, if you turn both of these on, both of the inputs will be off, which is a disallowed state. So what we have here is essentially 1 bit of memory. We can store 1 bit, either a 0 or a 1, in this, and it will be displayed on the outputs. And this will be very useful in future videos for building things like RAM and registers, as well as some other circuits which we'll get to later. So that's all for this video.